Welcome to this comprehensive guide on C-sharp tasks, asynchronous operations, and thread safety, designed specifically for beginners. We will explore how these powerful features enable you to build highly responsive, efficient, and robust applications. Asynchronous programming allows your C-sharp applications to perform multiple tasks concurrently without blocking the main thread, which is crucial for maintaining responsive user interfaces. This approach ensures that your application remains interactive even during long-running operations. This is especially useful for I/O-bound operations like network requests, file access, or database queries, preventing your application from freezing and enhancing overall user experience. By offloading these tasks, the UI thread stays free to respond to user input. Conversely, long-running synchronous operations can lead to a poor user experience by making the UI unresponsive, causing the application to appear frozen or crashed. This often results in frustration and a perception of slow performance. C-sharp introduces the task and task T classes as the fundamental building blocks for asynchronous programming, representing operations that may or may not return a value. A task signifies an operation that completes, while task T indicates an operation that yields a result of type T. The task-based asynchronous pattern, or TAP, is the recommended and most modern approach for handling these operations in C-sharp. It provides a consistent and simplified model for writing asynchronous code, replacing older, more complex patterns. The async and await keywords are central to TAP, significantly simplifying working with tasks and making asynchronous code much more readable and maintainable. They allow you to write asynchronous code that looks and feels synchronous. The async keyword marks a method as asynchronous, signaling to the compiler that it can contain await expressions within its body. This designation is a prerequisite for using the await keyword effectively. The await keyword pauses the execution of an async method until the awaited task completes, crucially, without blocking the calling thread. Instead, control is returned to the caller, allowing other operations to proceed. This mechanism significantly improves code readability and maintainability compared to older asynchronous patterns like the asynchronous programming model or event-based asynchronous pattern. It eliminates complex callbacks and state machines. You can create tasks using task, run to offload CPU-bound work to a background thread from the thread pool, or by defining async methods for I/O-bound operations. Both approaches enable non-blocking execution. To start a task and efficiently wait for its completion, you simply use the await keyword before the task call. This allows the current method to yield control until the awaited operation finishes, then resumes execution. For operations that are expected to return a value, task T is used, where T specifies the exact type of the return value. For instance, task string would return a string upon completion. Consider downloading data from a URL using HTTP client and async/await as a practical example of an I/O-bound operation. This demonstrates how to fetch web content without freezing your application's user interface. While async void is suitable for event handlers, acting as a fire and forget mechanism, it should generally be avoided for general asynchronous methods due to its limitations in error handling and testing. For all other asynchronous methods, it's best practice to use async task for methods without a return value or async task T for those that do. This ensures proper exception propagation and easier management. Avoiding async void prevents difficulties in exception handling, as exceptions thrown in async void methods are often lost, and mitigates the potential for deadlocks, especially in UI contexts. In library code, configure await is important to prevent deadlocks and improve performance by avoiding context capturing. This tells the runtime not to marshal the continuation back to the original context, which is often unnecessary in libraries. Cancellation tokens provide a robust mechanism that allows you to gracefully cancel long-running asynchronous operations. This is essential for resource management and user control, preventing unnecessary work. You initiate cancellation by creating a cancellation token source, and then pass its token to the asynchronous method. Within that method, you periodically check for cancellation using token.isCancellationRequested or token.throwIfCancellationRequested. Exceptions in asynchronous operations are handled using standard try-catch blocks. just like synchronous code. This familiar pattern allows you to manage errors effectively within your async methods. When await is used, exceptions are propagated from the task to the calling code, where they can be caught by a surrounding try-catch block. The await keyword effectively unwraps the exception from the task. You can also access exceptions that occurred during task execution through the task exception property, which returns an aggregate exception if multiple exceptions occurred. This is useful when not awaiting the task directly. Thread safety ensures that code can be safely accessed and modified by multiple threads concurrently without causing data corruption or unpredictable behavior. It's about maintaining data integrity in a multi-threaded environment. Race conditions occur when multiple threads access and modify shared resources simultaneously, and the final outcome depends on the non-deterministic order of operations. This often leads to unpredictable and incorrect results. Thread unsafety can lead to severe consequences, including incorrect data, application crashes due to corrupted memory, and even security vulnerabilities. These issues are often difficult to diagnose and reproduce. An example of a classic race condition is incrementing a shared counter from multiple threads without proper synchronization. The counter's final value will likely be less than expected due to lost updates. The lock keyword in C# protects critical sections of code, ensuring that only one thread can access a shared resource at a time. It acquires an exclusive lock on a specified object, preventing other threads from entering the locked block. It's crucial to release locks promptly by keeping the locked section of code as minimal as possible to avoid deadlocks and improve concurrency. Excessive locking can severely degrade performance. Mutexes provide exclusive access to shared resources not just within a single process, but also across different processes. They are more powerful than lock for inter-process synchronization, but also carry more overhead. The interlocked class offers atomic operations like incrementing, decrementing, or exchanging variables, which are inherently thread-safe without the need for explicit locks. These operations are highly optimized for performance. Thread-safe collections from the system. Collections, concurrent namespace, such as concurrent dictionary, concurrent queue, and concurrent bag, provide built-in safety for common data structures. They handle synchronization internally, simplifying concurrent programming. Immutable data structures, which cannot be modified after creation, are inherently thread-safe because their state never changes. Multiple threads can access them simultaneously without any risk of data corruption. A deadlock occurs when two or more threads are blocked indefinitely, each waiting for the other to release a resource that it needs. This creates a circular dependency, halting all involved threads. Common causes of deadlocks include nested locks where locks are acquired in different orders, circular dependencies where threads wait for each other in a loop, and resource starvation, where a thread never gets the resources it needs. To effectively avoid deadlocks, always acquire locks in a consistent, predefined order across all threads and strictly avoid nested locks whenever possible. This breaks the circular wait condition. Consider using lock timeouts to prevent indefinite waits, or reader-writer lock slim for scenarios with frequent reads and infrequent writes. Reader-writer lock slim allows multiple readers concurrently, but only one writer. Minimize shared state between threads to reduce the need for synchronization primitives like locks. The less data that needs to be protected, the fewer opportunities for race conditions and deadlocks. Keep the critical sections of code protected by locks as short as possible. This reduces the time threads spend waiting for a lock, thereby improving overall application concurrency and responsiveness. Prefer immutability for data structures and use thread-safe collections from system collections, concurrent whenever possible. These approaches inherently reduce the complexity of managing concurrent access. Thoroughly test your code under heavy load and concurrent conditions to identify potential thread safety issues. Concurrency bugs are often subtle and only manifest under specific timing scenarios. Here's an example demonstrating how to download data asynchronously using HTTP client and async/await. This code snippet illustrates a common pattern for non-blocking network operations in C# applications. This snippet shows updating a shared counter using the lock keyword for synchronization. It ensures that only one thread can modify the counter at any given time, preventing race conditions and ensuring data integrity. Here, interlocked, increment provides a highly efficient and thread-safe way to update a counter. This atomic operation avoids the overhead of locks for simple arithmetic operations, offering better performance. A concurrent dictionary is used in this example to store shared data safely across multiple threads. It handles internal synchronization, allowing concurrent additions, updates, and retrievals without explicit locking. This illustrates the use of immutable data structures for inherent thread safety. Since the data cannot be changed after creation, there's no risk of race conditions when multiple threads access it. Finally, an example demonstrating techniques to avoid deadlocks in your C# applications, such as consistent lock ordering. This practical example highlights how careful design can prevent common concurrency pitfalls. Understanding C# tasks, asynchronous operations, and thread safety is absolutely vital for building responsive, scalable, and reliable applications in today's multi-core environments. Mastering these concepts is key to modern software development. We encourage you to practice these techniques, experiment with the code examples, and explore further resources to master these essential C# concepts. Continuous learning and application will solidify your understanding and skills.